Hello. Um, Welcome to the to another video. Today, we're going to talk about relatively a bigger chapter. The title of the chapter is Properties of Maximum Likelihood Estimators, and basically this is a shift up from the last chapter titled Maximum Likelihood Estimators, and there is quite a lot of problems to discuss here, as well as a lot of concepts, so it might take longer than before. So I'll just kick off very quickly. Preliminaries. Whenever we're talking about maximum likelihood estimators, 4 important preliminary concepts must be reviewed. The first presents some stochastic models of time series and briefly discusses their properties. The second is concerned with convergence of a sample average to its population mean as t goes to infinity. This is known as the weak law of large number. The third identifies the scaling factor ensuring convergence of scaled random variables to non-degenerate distributions. The fourth focuses on the form of the distribution of the sample average around its population mean as t tends to infinity, known as the central limit theorem. So one important topic is that convergence of sample average to population mean. When sample average converges to population mean, asymptotically it is weak law of large number, and when sample average is distributed around population mean, asymptotically is the central limit theorem. 4 central limit theorems are discussed: the Lindbergh-Levi central limit theorem, the Lindbergh-Fowler central limit theorem, the Martingale difference square central limit theorem, and a mixing central limit theorem. So let's kick off very quickly. Properties of stochastic time series. In this section, various classes of time series models and their properties are introduced. These stochastic processes and the behavior of the moments of the probability distribution functions are particularly important in the establishment of a range of convergence results and central limit theorems. Okay, stationarity. A variable y is stationary if its distribution or some important aspect of its distribution is constant over time. Two commonly used definitions of stationarity are weak or covariant stationarity and strong or strict stationarity. Weak stationarity. The variable y is weakly stationary if the first two unconditional moments of the joint distribution function do not depend on t for all finite j. So property 1, when the first moment when the first moment uyt equals mu is less than infinity, which mean that mu is constant and finite. Variance, the second moment is constant and finite, doesn't change with time, and the covariance between yt and yt minus k, which is this lag, is a function of the time between the 2 points k and is not a function of time. So the first two moments are constant over time, and the third moment, which is the covariance, is not constant over, is not a function of time. So basically it's not necessarily constant over time. Consider two snapshots of a time series of equal length which are s periods apart, which can be represented schematically as follows: period 1 and period 2. Here y1j and ys plus 1 j plus s represent the time series of two subperiods. An implication of stationarity is that y1j and ys plus 1 are governed by the same parameters mu, sigma square, and the covariance stationarity. So okay, it's not, these are constant over time, this is not necessarily constant over time. Stationarity example: stationarity AR1 process. This is an AR1 equation. You already know y equals alpha plus rho multiplied by lag plus ut. With rho less than 1, this process is stationary because the mu equals alpha by 1 by alpha divided by 1 minus rho. Variance sigma square equals, well, sigma square divided by 1 minus rho square. Covariance sigma k equals sigma square rho k divided by 1 minus sigma square. Same, just rho k is added, are all constant and finite. Many densities are weakly stationary, including stationary ARMA models, where covariance, the third moment, is not constant over time. It changes with time, so these two are constant, but the third is not constant. Strict stationarity. The variable yt is strictly stationary if the joint distribution function given by f does not depend on t for all finite j. The strict stationarity requires that the joint distribution function of two time series s periods apart is invariant with respect to an arbitrary time shift, where actually it means all the moments are constant over time. That's all. So the strict joint distribution function is given here. A strict stationarity requires that all moments of y are independent of t. It follows that higher order moments such as, so this is a higher order moments, yt minus mu, yt minus k minus mu. So higher order moments such as this one, and then simply keep doing the square, must be functions of k only. Higher order moments are functions of k only, not t. Strict stationarity does not require the existence of the first two moments of the joint distribution of y. So if mean and variance is not there, this is fine. For the special case in which the first two moments do exist and are finite, mu sigma square less than infinity, so they didn't go up to infinity. That's, the joint distribution function is a normal distribution. Weak and strict stationarity are equivalent. Basically, strict stationarity becomes strict stationary if you don't have the first two moments, and if you have all the moments and all of them are finite, then it's strict stationarity. An example of yt which is identically independent and identically distributed with a Cauchy distribution, which is strict stationary but has no finite moments and is therefore not weakly stationary. Interesting. Cauchy distribution is strictly stationary where the covariance is invariant to time and is therefore not weakly stationary. Alright, let's see if it's recording. Yep. Okay. Now remember, in strict stationarity we don't need, as I said, the first two moments. The final moment, the covariance must be invariant to time. And a good example is Cauchy distribution, which is strictly stationary but has no finite moments and is therefore not weakly stationary. So it doesn't have mean and variance, but it has covariance which is invariant to time. Another example is an Eiger's model, which is strictly stationary but has not weakly stationary because the unconditional variance does not exist. So it has mean and covariance but not variance. Multiangle difference sequence. A multiangle difference sequence is defined in terms of its first conditional moments having the property, well, the mean of the lagged yt equals 0. This condition shows that information at time t-1 cannot be used to forecast yt. So basically information at time t-1 and time t remains not same. It cannot be used Two important properties of a martingale difference square arising are expected mean of yt equals 0 and expected covariance, and which is unconditional mean of the martingale difference square is 0, which follows by using the law of iterated expectation. And the second property shows that the martingale difference sequence is uncorrelated. MDS is uncorrelated with past values of yt. So yt minus k equals 0 is uncorrelated with past values of yt. However, it does not necessarily rule out higher order moment conditions. What are the examples? Nonlinear time series. Consider a nonlinear time series model sorry, where yt equals ut minus 1, so this is multiplied. Nonlinear, it is a martingale difference square because the unconditional moment, unconditional mean of the martingale difference square is 0 here. Since mean of the lagged value and mean of the current value 0, the process yt nonetheless exhibits dependence in the higher order moments. For example, so unconditional so not necessarily yt minus k or the yt is not correlated with higher order moments is not true. In higher order moments, yt minus it might be correlated with yt minus 1. So covariance of yt square and yt square minus 1 does not turns to 0, might be correlated. So in higher order moments, the process MDS is not necessary to be 0. Autoregressive, and another example is autoregressive conditional heteroscedasticity. Consider autoregressive conditional heteroscedasticity Arch model where yt equals alpha naught plus alpha 1 y square minus 1 root over zt. Okay, so this is rho 1 yt square minus 1 is a common equation. Y square minus 1 z is IID, 0 mean so uniform distribution. Now yt is MDS because the mean unconditional mean is 0. The process nonetheless exhibits dependence in the second moment because the unconditional variance, which is the second part, is not necessarily 0, rather it becomes it is 1, because again 0 and 1 is already given, so it is 1 the second moment. So it is in contrast to the properties of stationary time series. A function of MDS is not necessarily MDS. So a function of martingale difference square might not be a martingale difference square itself. So stationary, we have talked about stationary, and we have talked about martingale difference square for non-linear time series and autoregressive conditional heteroscedasticity, where you cannot, in martingale difference square, you cannot use the past values to derive to the current value, or you cannot use martingale difference square for forecasting. White noise, if we want a process to be white noise, its first and second unconditional moments must satisfy the following properties. White noise is a special case of weakly stationary process with mean 0, constant and finite variance sigma square, and 0 covariance between yt and yt minus k. MDS with finite and constant variance is also a white noise process. So it's a special case where the mean is 0, the variance, where the mean 0, the variance is constant, and covariance is 0. See the difference? Mean and covariance are both 0, but variance is constant. MDS with finite and constant variable is also white noise, since the first unconditional moments exist and the process is not correlated. Okay, this is white noise. Hmm. So as we were saying, if a martingale difference square has a finite and constant variance, it becomes a white noise process because it has mean and variance and is not correlated. If a MDS has infinite variance, so it's not finite, then it is not white noise. Very simple. An example is bilinear time series. This is a bilinear time series model where we can see it's a non-linear, in the variance is non-linear, same as before. See, non-linear and non-linear. So it's a non-linear time series in which delta is a parameter. The process is white noise because mean 0, variance is constant over time, covariance is 0. Every term contains at least two disturbances occurring at different point in time in the last step. However, yt is not a martingale difference square because if the lagged mean, if lagged or the lagged mean is not equals 0, it is supposed to be 0, so it's not a martingale difference square. And then a mixing property. As a martingale difference sequence are uncorrelated, it is important also to consider alternative processes that exhibit autocorrelation. Consider two subperiods of time series s periods apart. So first subperiod yt minus 2 yt minus 1 yt, second subperiod yt plus s plus 1 yt plus s plus 2 yt plus s. Two subperiods in which yts equals yt plus 1 up until ys. So as we were talking about, martingale difference sequences are uncorrelated. It is also important to consider alternative process that exhibit autocorrelation. So we are considering two subperiods. Here in yts, if the two covariance of these and these goes to 0 as s tends to infinity, where g and h are arbitrary functions, then as they become more widely separated in time, they behave like independent sets of random variables, which is known as, this process is known as mixing, technically alpha mixing or strong mixing. So as they tend to infinity, they become independent sets of random variable. So we are just talking about two subperiods of time series. So this is 1 to 10, this might be 31 to 40. They're the same time series, but as they tend to infinity, they behave like independent, and so is known as mixing, technically alpha mixing or strong mixing. A concept of strong stationarity and mixing have the convenient property that if they apply to yt, then they are also applied to the functions of yt. An IID process is mixing because all the covariances are 0 and mixing conditions are trivially satisfied. Okay, a moving average process with Q lag with IID distribution is mixing because it has finite dependence, so that 2.2 is satisfied for K greater than Q. The AR1 process is mixing since the covariance of yt and yt minus k decays at an exponential rate as k increases. So for AR1, covariance will decay between yt and yt minus k. For moving average with Q lags, it has finite dependence. The dependence is finite dependence. Okay, Then comes weak law of large numbers. The stochastic time series model discussed in the previous sections defined in terms of probability distributions with moments defined in terms of parameters of these distributions. As maximum likelihood estimators are sample statistics of the data in samples of size t, it is of interest to identify the relationship between the population parameters and the sample statistics as t tends to infinity. So y1 to yt represent a set of t IID random variable from a distribution with a finite mean. Consider the statistic based on the sample mean. The sample mean y bar equals mean of summation of yt. The weak law of large number is about determining what happens to y bar as the sample size t increases without limit. An example of weak law of large number is exponential distribution. Gives the result. This one gives the result of simulation experiment from computing sample means of progressively large sample size like t to 500, comprising IID draws from the exponential distribution y by mu, exponential of minus yt by mu. Population mean is 5 for relatively small sample sizes. Y is quite volatile. Y mean y bar, the sample mean is quite volatile but settles down as t increases. The distance between the sample mean and the population mean eventually lies within a small band of length r is equal to 0.2. That is, the difference between sample mean and population mean is less than 0.2 as represented by the dotted line. So basically what it suggests, at t tends to infinity, they try to converge, they attempt to converge. Now this is page 7. Let's go to the exercise. So the first exercise is weak law of large numbers, sample, the one that we just talked about, and we need to process the repeat this process. Let's have a look in MATLAB and in R by and let's minimize this. Okay, let's see if there is any local function. No, there is no local function. It's a very simple code. Let's go through it first. Control L. We're trying to demonstrate law of large number. So clear all CLC. Again here RM. Remove RM means what? RM is this is remove objects from a specified environment. So RM, starting the bracket list equals is in the bracket all equals true, is all equals true. So RM list equals is all equals true. Graphics dot off. Then we need to load any compatibility requirement. Interesting. Now you see there's a ease of use in R compared to MATLAB in terms of developing doing simulation. We need to pass the command in MATLAB random string set. This is global stream, not default stream. This is because it has updated. Stream random stream t1 and then seed 12. Here just set dot seed 4, and we need to use this kind Marcena twister. We need to use this kind Marcena twister. You can find more details on it. Let's see. It's not updated. Let's do it again. There might be, or we can try doing this, I'm not sure. there is no document for this, but there is document for set sheet. Random number generation, where we can see, where we can probably see random number generation has the types of kinds. Default, if not default, we can say it. See, Wishman Hill, Marsegilla Multicurry, Super Duper, Marsena Twister, Growth Taco. There's a lot of kinds we can use, so just gonna keep Marsena Twister and seeding up to 4. Mean population mean 5, total observation 500. Then generate random numbers from a gamma distribution. So G passing gamma distribution is 1, random G from a gamma distribution. Okay, 1 and T1. This line means we are generating T by 1 array of values drawn from gamma distribution with shape parameter 1. Here is just T, R gamma is just T, which is again the same thing, T by 1 parameter of values, T by 1 parameter of values, T parameters with shape 1. And y equals mu into E, y equals mu into E. That's all. Basically we are generating numbers of mu that is based on the gamma distribution. Then generate sample means from sample size T equals 1 to 3 to T max. So I have zeros, T rows, 1 column, array. Here we are passing the array command instead of directly zeros. Array is 0 and the matrix is array is T rows in 1 column. Very simple. For 1 to T, y bar equals mean of y. So in y bar we are putting the mean of y for all I. Sample mean, generating the sample mean for I in sequence T up to I in sequence T means 1 to T. Y bar passing mean, we are passing into y bar mean of all y from 1 to T, mean of all y from 1 to T. So we generated exponential random numbers from gamma, generated sample means from sample size, and then comes plotting. So 1 to T sequence 1 to T pi by 1, plot is x is tt, y is mean to, in terms of y we put y bar. Here we have calculated y bar too, 1 zeros 1 column. I'm just putting it again, not necessary. Mean to 1 zeros 1 column. Type line graph, color dark blue. This is the main title. These are the other stuff. This is the main title. Just have a look. Expression of bar y. 7.5. Y level, X level. We are setting the axes. If we run this, let's see what happens. Okay. Running these, we have the law of large number plot. The law of large number plot, where the lines, there are 3 lines. One is mu, and replication of, I'm not sure what does it mean. Let me see. Replicate elements of vectors and lists. So we're replicating the elements from 1 to t, which is this one, tt against y bar, which is this one actually, yeah, tt y bar, replicate elements up until t. Then the second is 4.80 multiplied to 1's t1, 4.80 multiplied to replication of 1 t times mu multiplied to 1's up until t times 4.80 multiplied to 1's up until t times, and 5.20 multiplied to 1's up until t times. This is coming from the question actually. This is coming from the question, that's all. So we are plotting this, and these lines are shown, have already shown that we have seen. Okay, so this was our first problem. Let's look into the second problem. The second problem is sufficient condition. A sufficient condition for weak law of large number to hold yt mu and variance 0. So we have finite mean, but variance of sample mean is 0 as t tends to infinity. Compute the sample moments. This is the sample moment mi equals y divided 1 divided by t, which is the mean, multiplied to which is simply the mean of y. That's it, which is simply the mean of y, because summation divided by t. And this is t. For t, IIT draws from the uniform distribution is 1, illustrated by simulation. Repeat part A using the student t distribution. So with mu0 2 degrees of freedom, v0 3, and where the first two population moments are mu, and we have a variance. Now the variance is not 0, the variance is, there is a variance, v0 divided by v0 minus 2. Confirm that weak law of large number holds, and we need to repeat these parts for v0 4 and v0 equals 5. Okay, great. So again we start off with passing the simulation command, and we have to fix this one again. This is global stream, not default stream. It's not gonna work. 12 kind Marcena twister, see the same. So t equals 100 observation, n equals 5000, t equals 100 observation anyway it must be somewhere. T equals 100 observation, 100 observations, m equals 5, n equals 50,000. we are passing these numbers. Then comes the moments, m1 m2 m3 m4, because we're gonna calculate all these moments with in loops, so we're passing zeros in them. So first moment for I equals 1 to n, let's generate the numbers. First let's generate the sample. Random t rows on column, minus 0.5 from each, zeros, replication of 0 n times, replication of 0 n times. Okay, instead of writing every time, just passing them in, replication of 0 n times. Progress bar, oh, this is just to show progress bar, it's not essential. For I in sequence n, sequence n means 1 to n, y from simulate y from a uniform distribution point minus 0.5 to 0.5. So run if t, run if is instead of random, we do run if, same thing. So random t generate minus 5, mu 1 I summation of y1 divided by t into y square y cube y to the power 4, because it's uniform distribution drawn from uniform distribution when the function equals 1, so there is no nothing. So here again we're just setting progress bar, not necessarily, but it's nice to know. Format short g. So then just writing things up, sample size est, so mean of m1 is the mean of m1 that we have generated, and then the standard deviation is the variance squared is the variance of m1. See, we're passing n within inverted commas, then we're calculating the mean and the variances for m2, m3, m4. That's all that has been asked in this question. mu naught 2 degrees of freedom v naught 3, confirm that this one holds. Okay, fine. So basically the problem that we have solved is when we are repeating parts for v naught equals 4, v naught equals 5, where we're checking if ln holds for m3 but not m4, m1, m2, m3 for all. And if we want to do t distribution instead of uniform distribution, this is the code 2 plus trend 3, 2 plus trend 3, which should mean first we need to generate r new. I think we need to generate r equals trend, then we just have to put this one 2 plus trend 3 t1, where yeah, because the function is, this is the value of new, this is the value 3 is coming from v naught, this is v naught 3, or new, sorry, that is new, and m rows in columns, so mn, that's all, very simple. So here it is 2 again new, and rt instead of trend we put rt, t rows, and this is again new 3, 2 plus, just this is sequences automatically in R, the sequence is automatically generated when we pass t, and here we are passing new. So we started with new, then we passed the size, here we just pass t, automatically size is developed, and new, and so to adding it to with the equation, and every time we're simply checking if the question problem is solving if ln holds only for the sample mean m1 weak of large number but not m3 and m4, if they're for m3 but not m4, or they're holding for all. So that is what it is being checked. Okay, this being done, let's go into the next phase. Okay, up until now the problems that we have solved, we're gonna discuss more into the problems. So y bar is sample mean is a random variable, the value of which in any single sample need not necessarily equal to mu. So sample mean is not necessarily equals to population mean, but as t tends to infinity, the sample mean converges to population mean, or they're very close enough to the value property. So this is called limit in probability sense, or lim PR. So which is less than r equals 1. When r is greater than 0 is less than r equals 1. So the difference when t tends to infinity equals r, or more compactly, the limit in probability sense for sample mean equals population mean when t tends to infinity. So simple mean converges in probability to the population mean. That can also be written with this: the simple mean converging to population mean converges in probability. For higher order moments like yt to the power I, this is also true. A necessary condition for weak law of large number to satisfied is that population mean is finite. So a sufficient condition is that simple mean converges to population mean. As it converges to population mean, the variance of the simple mean turns to 0. So we have a finite simple mean but no variances, so that the sampling distribution of the mean converges to a degenerate distribution with all its probability mass concentrated all the population mean. Example: uniform distribution. Uniform distribution is, as we know, minus 0.5 to 0.5. It has the function value is 1. The first four population means are, as we can see, 0, 1 by 12. The first four the second one is 1 by 12. Third 0, fourth is 1 by 12. So given these values, we can actually analyze the simulated results. Okay, there is more. If sample mean y to be means of two sample size t, then population means mu1 and mu2, and c is a continuous function not dependent on t, then as you can see, plus minus of y1 y2 equals this is equal to population means plus minus multiplication of sample means equal to population means. This is what we have already done. The results, you see, just a few minutes back we did this, and as we can see, as t tends to infinity, the means become more constant, you see. And this one for odd numbers, what is happening? For odd numbers we are having plus and minus. For even numbers, they are exactly the same, and the variances are getting closer to 0. So the weak law of large number is being held. Third property is the deviation. If mu2 is not equal to 0 equals, and the Slutsky's theorem suggests p limit c y bar c p limit y bar. So these equals to each other. So Slutsky's theorem in vector cases, assuming only that the variance is of yt is finite for all t variances. So variance of y equals y by t square for variance, that equals to first the variance portion, summation of the variance of y divided by t square, then 2 multiplied to covariance of yt minus s divided by t square. Or if yt is a weakly stationary, and we can write the covariance as gamma, then it simplifies to, you see, 1 by t gamma naught 2 by t. This is the part 1 minus s by t, s equals 1 to t, 1 minus s by t gamma s, where gamma s is the covariance of yt minus s. Yt is either IID or MDS or white noise. If in any case gamma s, this one turns to 0, which is the second portion, the third moment is completely 0 in all cases, and we have the variance simply the first part yt minus the gamma naught by t, which turns to 0 at as t tends to infinity, and WLLN holds. What is autocorrelated condition is that gamma s turns to 0 as s tends to infinity. In that case we have to take the second part yt 1, just take the second part 1 by t, 1 minus s by t, 2 is not necessary here. Gamma s is less than 1 by t, 1 minus s by t, absolute value of the gamma s, So we are just moving forward from here, where as we know, as gamma s turns to 0, so this portion is turning to 0 as t tends to infinity. That has been proved. This is turning to 0 as t tends to infinity because this part is less than 1, because this part becomes less than 1 as t tends to infinity. And the last step uses C0 summation. Sequencity satisfies if AT tends to AT tends to, then this is C0 summation. As t tends to infinity, AT turns to A, or this is the same thing, mean of AT turns to A. This implies the variance will disappear as t tends to infinity. Thus, any weakly law of large number, any weakly stationary time series whose autocovariance satisfy this, the gamma s portion as s tends to infinity will obey WLLN. And if it is strong with strong mixing, applies to general class of processors. Examples are autoregressive model 1. So sigma square 1 by rho square multiplied to rho s. As gamma s turns to 0, s turns to infinity, it clearly satisfies. This shows WLLN will hold because this portion will turn to 0. Now let's just check Slutsky's theorem. What was the problem? Again, this is a youth chapter, as I have already suggested. What was the problem again? In Slutsky's theorem, consider the sample moment given by the square of standardized mean, in which y equals y sample, just passing the mean of yt. A square is yt population mean minus sample mean whole square, and their mean. Simulate the statistics 5000 times for sample sizes, given sample sizes comprising I redraws from the exponential distribution with mu2 variance for given limit in probability sense. This equals 1. So we just need to demonstrate Slutsky's theorem. If Slutsky's theorem does not hold, then m equals root 2y. We repeating show that if Slutsky's theorem hold for this equation, discuss why the theorem fails in this case. Okay, let's have a look. So this is the Slutsky's theorem. Again, there is no local function. We start with, as we always do, set.z, t is 10, n is 50,000 or 5,000. I'm not sure, they are so confused. Okay, I think it is done as wishes. 10 observations, replications are 50,000 replications. There are 5,000 times. Simulate the statistic 5,000 times. So this is simulation replication. Mu is also given in the question. Yeah, mu2 variance for mu2. So first we need to, for both m1 and m2, we need to, for both sample and population means, actually we need to pass zeros, replicate 0 n times, pass them in, generate exponential random numbers from gamma distribution. Mu, as I already told regarding gamma distribution, this is t rows, 1 column, the size, and this is the shape of gamma distribution, which is 1. For your R model, sequence I 1 to n is expressed with sequence n. R gamma mu into R gamma t is t1 itself, and 1 is the shape mean to that. So m1 is the first equation, mean y divided by mean y divided by this one, sorry, standard deviation, mean y divided by standard deviation of y squared. mean y standard deviation of y squared, so SD instead of STD. It will roll square root t multiplied to mean y square root of t. Now this is the second part. Oh, there are two m's. Square root of t multiplied to y mean y squared. Close. Now after we do that, then just express, let's just express our results with this, that's all. You see sample size, first we pass it, okay, then moments of results for M2 is given, mean of M2, standard deviation of M2, mean of M1, standard deviation of M1, all are given. I mean all are calculated. So this is very simple, and we just need to compare this mathematically if Slutsky's theorem holds. For 50,000 replications. See, variance of M1 is less than 0, but variance of M2, for variance of M1 WLN holds, for variance of M2 WLN does not hold because it's going up and this is dropping. That's all that we needed to see. Great job. We have gone through quite a lot of stuff by now, and we have reached a very important part in this chapter, which is introducing us to gradient Hessian information matrix, which we will constantly require in our following chapters. The gradient function at observation t is this, as it's been shown, is this. Mean of the gradient is 0. We need to always remember that. And there is a proof why mean of the gradient 0 with the probability distribution looks like this. We take the function which is a probability distribution, then we differentiate both sides and this becomes 0, that's all. We do interchangeability regularity condition R5 and natural logarithm combined. The left hand side of the expression becomes the function of gradient. So basically the mean of gradient is 0, variance of gradient, the second property, is negative Hessian. So GT transpose is negative Hessian. So again, it has been shown out, the proof has been shown. You can look into the book for further details if the proof is not necessary at this stage. Once again, evaluating the expression. So basically we have, from these calculations, we have the covariance of gradient, and added to the Hessian, we take it right hand side, it's negative Hessian. So now some applications. Look into Poisson distribution. For Poisson, so our gradient here is yt theta minus 1 for Poisson distribution, and Hessian is minus yt divided by theta square. So at first we initialize with theta naught, and then we find the gradient turns to 0. For Poisson distribution, G transpose is 1 by theta, and Hessian is minus 1 by theta. Very simple, so gradient equals minus Hessian, that's all. For Poisson distribution, we can do G transpose, we can put that to J, which is the outer product of the gradients matrix. So then information matrix, very important. This J that we have already talked about, which is the outer part of gradient matrix, is also known as information matrix, which also is negative Hessian. It represents a well-known information equality. Information matrix represents a measure of the quality of the information in the sample to locate the population parameter theta. For log likelihood functions that are relatively flat, the information in the sample is dispersed, thereby providing imprecise information on the location of theta naught when the log likelihood function is flat. But if the log likelihood function are less diffused, and if it is more concentrated, it provides more precise information on the location of theta naught, which is which is the case we always see. So if negative Hessian represents information, the sample size is t multiplied to the information matrix equals, so we have to multiply t with information matrix which equals negative Hessian. Another example is Bernoulli distribution, theta yt 1 minus theta 1 minus yt. This is a Bernoulli distribution, which is a uniform distribution located within one, where the gradient, first and second derivatives, the gradient is 1 minus yt 1 minus theta 1 minus yt 1 minus theta. For gradient, for Hessian, 1 minus yt divided by 1 minus theta whole square. That's all, no difference. Information matrices, so you have gradient, we have Hessian, we have information matrix 1 divided by the initial theta naught multiplied to 1 minus theta naught. Because this is the mean of the Bernoulli distribution, the total amount of the sample, we just multiplied both sides with t. For a normal distribution, this is the log likelihood function. We all know 1 by 2 population parameters, mu sigma square 1 by 2 log twice by 1 by 2 log sigma square 1 by 2 sigma square y minus u. The gradient is, first comes yt minus mu by sigma square, which is coming from this part, and then from the log likelihood function, the next part 1 by 2 sigma square minus 1 by 2 sigma square, sigma square minus 1 by 2 sigma square plus 1 by y by mu sigma square 2 sigma square to the power 4. Okay, so first difference and second difference on this. So you take the first difference, then we again take the second difference, so you get this too. Hessian is what it looks like this, so they are equal, yt minus mu by sigma 4. This is the thing we are concentrated with. And so information matrix become t by sigma square, t by 2 sigma to the power 4. This might be helpful. So let's have a look into our problem now. Let's have a look into what page we are in, page 27. What page is the problem? The gradient Hessian problem is located in page 48, page 27 and page 48. Okay, consider random sample of size IID 1, derive gradient Hessian, compute the statistics, information matrix must be derived. We need to do these for exponential distribution too, so let's just keep it open. 27 might need information from here. Let's have a look in R and MATLAB. Again, random stream set, global stream. I'm saying it's not default stream, it's a global stream. Set seed, we use the same kind. First, normal distribution, properties of gradient function, we need to create the data. In question it says mu equals 1, we use that. Sigma square equals 1. Let's have a look into it again. No worries. Sigma square is equal to 1. Mu is always 1 here. Unknown mean theta, known variance 1. But this is what we are trying to prove. Mu is 1 from our equations. So mu is 1, sigma square 1 equals to random. We are creating a random number u, t rows 1 columns, r non t automatically creates it. Mu plus sigma square, square root of sigma u, okay, sigma let's go to page 27, and what do we have? Okay, 13 48, no, Right. Square root of sigma square multiplied to u. This is the regular equation, normal distribution equation that we have already seen. Let's have a look into it if you want to check the normal distribution equation. See, y minus mu square. So mu plus square root of sigma square. Mean, m is mean of y, maximum likelihood estimate. Gradient E is y minus mu divided by sigma square minus mu divided by sigma square. Hessian is minus 1 by sigma square minus 1 by sigma square, and information matrix is simply gradient multiplied to gradient inverse. Now this is important. Tg minus Tg, this is multiplication sign, multiplied to G minus Tg. So instead of inverse we are putting minus T. Let me see if there is anything found. Arithmetic operator. Okay, see xyy, which means for r can be used for non-integers. 1 divided by 0.2 or squared 1 multiplied to can be used for non-integer y, if y is a non-integer value. Because this is a non-integer, because these are all variable series of data, 1 divided by 0.2, but the result is a representation error in some platform 4, but most platform give 5. 1 divided by 0.2. Okay, I don't want results in integers, rather I want the results in non-integers, the way I want to see the results. Because of that, outer product of gradient, I'm just putting percentage multiplying minus t. On the other hand, it's not mentioned anywhere. Okay, it's not minus t, I'm sorry, what am I doing? Control Z. Matrix transpose. See, now it's easy. So it's transpose of gradient and gradient multiplied, and this is the results gradient vector Hessian information matrix. Exponential distribution, this is normal. Let's look into exponential, where theta was 2 for exponential distribution. Where is the normal? Okay, let's just not scroll through, rather remember it. Anyway, exponential distribution, where there are two parameters, theta has two parameters. First, we gamma random variable. We need to prepare a gamma random variable. I'm not sure what this is. Let's see. Oh, shape 1 scale 1. So shape 1 scale 1, t rows 1 column, theta y minus mu, y divided by theta minus 1. This remains the same. Y divided by theta, y divided by mean is theta. Not necessary. Shape 1 scale 1, t rows 1 column, theta minus y with theta minus y. Okay, 1 minus 1 divided by theta square is the Hessian, and this is that's all. And can we run this and see what happens? See, gradient vector Hessian information matrix, all are calculated, so we calculated all. Okay, Now we are going to address the problem that comes next, which if page 48, if we go, remember page 30, page 48, we're gonna do sample mean assuming normality. No, not this one. We're gonna skip a few, these are not necessary. Asymptotic normality, efficiency property, I'm not sure, we can go through it. So basically consistency property of normal distribution. So we're gonna look into consistency of sample mean assuming normality. So this is 6. Consistency property of maximum likelihood estimation. We need to generate data with simulation, plot the mean for t is equal to 5000. What happens we will see, and that is the point of this exercise. Theory behind. Let's go to page 28. Asymptotic properties. We're just gonna leave consistency discussion. For normal distribution, this is the normal distribution equation, as we already know, 1 by root over 2 pi sigma square exponential of minus yt minus mu whole square divided by 2 sigma square. The converges to 1, population mean converges to 1. This is equation for Cauchy distribution, which we can use later but not necessary. 1 by pi, we just need to change the function, that's all. Normality is when the gradient turns to 0, the sample gradient turns to 0. Asymptotic distribution, to establish the asymptotic distribution of MLE, the mean value expansion of this condition around theta is this. This is highly used, you have to remember it. Gradient, mean of the gradient plus mean of the Hessian theta minus estimated parameter minus initial parameter, estimated minus the initial. So theta star lies in between, estimated and initial values, and both turns to theta naught as t increases. Root over t, as we can see, this is inverse, and this is basically G transpose. In between we multiply the Hessian all the time. So this is Hessian gradient, and omega naught. With omega we represent our information matrix. Inverse of the information matrix is represented with omega. Maximum likelihood estimator has an asymptotic normal distribution with mean equal to the population parameter theta naught, and covariance matrix equals to the mean of the omega, or simply that, mean of the omega 1 by I theta naught. Inverse mean of the omega, or simply mean of the inverse information matrix. Asymptotic variances of theta naught are obtained from the diagonal elements. The variances are found in the diagonal elements of the covariance matrix of this one. We have to remember that. In case of Poisson distribution, Hessian is minus 1 by theta or minus I by theta. I inverse equals theta naught. Example 2.25, simulating this for 5000 applications. This is what we plan to do, but the population mean is, now we need to normalize a standardization using the population mean. Theta 1 is population variance, theta initial value square divided by t is equal to 1 square by t, yi minus 1 divided by root over 1 square by t. The sampling distribution, the result suggests the sampling distribution z is skewed to the right for t equals 5, this mimicking the positive skewness characteristic of the population distribution. If we increase the sample size to 100, this reduces the skewness. Okay, let's look into the code now. Okay, there you go. And first we do the simulation. We set the simulation property. This is global stream, not simple stream. Marcena twister is the kind for R with setting 1, 2, 3. Remember, the numbers that we put after seed is the numbers that will generate the same random number. So if we change that, we will get different random numbers. So number of observations 5, mu1, or number of replications are basically 500. Population mean is given 1, variance is given 2, generate sample mean from size. So loop, first we store in YB, so create YB 0 rows 1 column, or replication of 0t for 1 to t, sequence t, or here for RT in sequence t, mu the square root of sigma square multiplied to random number t1. This is the regular normal distribution function. Random or R normal, and whatever we find, the mean of this goes in our replication. This goes in our replication, third bracket in the replication. That's all. There you have it. Then we create the graph 1 to t 1 to t mu into 1's t1. So basically mu is generated t times, so 1 to t, and then yb instead of this just mean. Is this the same thing? Mean against this consistency expression. Another line is added to it. Plot t mu into replication. Oh, this one is this. We are plotting this one against this one. This one is this. That's all we need to remember. We're plotting this against the line. Is another line added is this. So that's all. Mu 1 t1. Okay, so there goes your asymptotic normality. Now we plan to check for the efficiency property of maximum likelihood estimators. Exercise demonstrates the efficiency property where 10,000 replications are generated with t equals 100 observations from a normal distributions. Mean is 1, variance is 2, sigma square is 2. For each 10,000 replication we need to compute sample mean and median. After that we also compute the variance of the sample mean. Around 1 is simply 1 minus mu square divided by 1 by 1000. That's all. So result the theoretical, and compare the result. The theoretical solution of variance is sigma square, which is 2 by t. This one should equals this. Compare the variance of sample median, and with the theoretical solution pi sigma square theta by 2t. Use the results in C and D to compute if the variance generated with mean is less than the variance generated with median. That's all. Very simple. This is efficiency property of maximum likelihood estimator. An important learning in efficiency is Cramer-Rao lower bound, which provides a bound on the efficiency of estimator. Asymptotic efficiency concerns the limiting of value variance of any estimator, say theta hat around theta naught, as the sample size increases. So Cramer-Rao lower bound provides a bound on the efficiency of this estimator. Cramer-Rao lower bound suggests, well, starts from the beginning. Suppose if initialized theta parameter is a single parameter and theta hat is any consistent estimator with asymptotic distribution which tends to 0 and omega variance, omega is greater than or equal to the inverse of information matrix, or I theta naught. That is what Cramer-Rao inequality states. That's all. For now, just remember that the squared correlation between this one and gradient satisfies correlation. Squared correlation is less than or equals 1. That's all. Variance t theta is covariance of root t theta hat minus theta naught. The first element then the second element with gradient divided by the second element gradient. This is Kramer-Rao lower bound. For a vector parameter, Kramer-Rao inequality is simply inverse of omega is greater than or equal inverse of information matrix. Inverse of if information matrix, they are the same. So we can see in a normal distribution, information, first we need to find information matrix diagonally located in Hessian. Evaluating the expression theta equals theta naught, we just bring in we just take mean of an inverse of the information matrix. There you have it. If we do that, just simply take the inverse of this and multiply to the mean. The asymptotic variances are sigma square by t, and mean is this and variance is this. Very simple. Variance is this and okay. Now let's do the problem of efficiency testing. Very simple. Starts with, again, this was not necessary. You see, they made it a bit difficult because they're doing putting seed into for random number and for RNDN. It's not necessary. We could have just simply gone with random stream set global stream. This is just another way to express that. Everything else remains same. Remove object, least equals is all true, graphics dot off, then comes set seed on kind Mersenne twister. Mu is given, sigma square is given. There are 100,000 replications for 100 sample size. Generating simple mean. First we always need to generate u residual random with random number of uniform distribution 0 1. Generate simple mean. Let's see what they did here. It's a for R, first t times random number t rows r columns. Okay, t rows, we want t rows and r columns. My god, we wrote 100,000 columns. So now we have to make a matrix t rows r columns, where number of rows will be t, number of columns will be r. Number of rows, first random number, we are passing in the command to create a random number within 0 and 1 across 100,000 columns, where the number of rows will be t, number of columns will be r, and we create a matrix with that. Okay, so that is the trick in this code. Remember that. Much more easy in MATLAB. Or first pass the command that you want the random number, MATLAB part, then tell me R is saying tell me how many rows and how many columns you need again. Then you want them in a matrix format, put them in matrix. Okay, generate mu and in mu rows and sigma square random numbers. That's the equation y. It will automatically generate that. This is we're not generating random numbers, we're calculating with using the random number we have generated earlier. Mean is simply mean. Okay, apply is a function. Apply is a function that we use for apply is a function that we used on any array for any kind of statistical calculation. Apply y to apply function x margin function. X margin, a vector giving the subscript. For a matrix, 1 indicates row, 2 indicates columns. 1 indicates row, 2 indicates, so across the columns. We want to take y, and across the columns we want this means, across these columns we want the median, then we want the variances of these mean minus mu square, variance of the median. So basically then we just run it. theoretical variance of the sample mean, variance and median, and see if any of them. My question was to compare which one. We just need to see which one becomes. The problem was to see, if because it's an efficiency test, problem was to see if the variance of mean is less than the variance of median or not. That's all. Very simple problem. So that's it. Variance of mean and variance of median calculated. Very good. There you go. Simply and easily. The next case is checking asymptotic normality. What was the problem? The problem was exponential distribution, asymptotic normality. The exercise demonstrates the asymptotic normality of the maximum likelihood estimator of the parameter of the exponential distribution. So first we need to generate 5000 samples of size t is equal to 5 from the exponential distribution with parameters theta naught 1 by theta. So this is the exponential distribution function. We need to compute maximum likelihood estimator using the property that exponent has mean theta naught and variance theta square. Compute standardized statistics. We need to do that, and we need to plot the empirical distribution z using a histogram. That's all. Okay, let's have a look very quickly. Let's not waste a lot of time here. Asymptotic normality, again 5000 replications. Theta 1 is given, isn't it? Yeah, theta 1 is given, parameter theta 1. For sample t is equal to 5, we need to create a random number t rows, generate uniform random numbers t rows for 5000 columns. Here again random number, first function is random number, and we are passing number of rows t, comma, we can pass number of columns to it, will automatically generate, I guess, otherwise. Uniform random numbers within 0 and 1, and then we create a matrix. Theta multiplied to log 1 minus u log of 1 minus u. So we just take a log function, then becomes minus theta log of 1 minus u. Exponential distribution. Let's see if we can find it. Nope. Okay, just remember that 1 minus u, y bar mean y. So we are applying, finding y bar, this is y, realization of y, then mean y. We are applying, then square root y bar minus theta by square root standardized random variable, standardized y minus theta by root over theta square. Standardized random variable is being created, square root t, same thing here, divided by square root. See, the element wise is not there. For sample size of t is equal to 100, we do the same thing again, and then we generate the graph to see the difference, because the problem suggested interpret the shape of both cases. That's all. That's what we have done. I'm not gonna go into details right now. Next case is central limit theorem application, student T distribution. The exercise investigates the moment conditions required for the Lindbergh-Levy central limit theorem to hold when the population follows a student T distribution. So Lindbergh-Levy central limit theorem, we just want that to hold. Very quickly, let's go to Lindbergh-Levy central limit theorem. Let yt represent set of t id random variables from distribution finite mean, finite variance. The Lindbergh-Levy central limit theorem for the scalar case is this. The difference n tends to 0. The difference tends to 0, where d represents convergence. In terms of standardized random variable, simply divided that by sigma and the variance is 1. Alternatively, the asymptotic distribution is given by this, where signifies convergence of the A signifies convergence of the asymptotic distribution. In case of asymptotic distribution, mean is mu, variance is sigma square by t, or the mean of sigma square. So basically that's Lindbergh-Levy central limit theorem. An example is uniform distribution itself is a Lindbergh-Levy central limit theorem, where the variance is 1 by 2, isn't it, because sigma square by t. So if there are like 12 information, mean is 12, that's it, finite mean. Uniform distribution, which is equal to shown in panel. Okay, so Lindbergh-Levy central limit theorem, Lindbergh-Levy central limit theorem. Now let's have a look into this Stearns T distribution. We're gonna do T distribution on it very quickly. First, we know the equations already. Have gone through equations very quickly. This is the first part, remains same. Load the helper function, 500 observations, 5000 replications. Nu is equal to 1, that is given in the question. Okay, nu is 1, 2, 3 degrees of freedom. They are the degrees of freedom. So we're gonna start with 1. Chi-square is random number t rows are squared. Random number we're generating number for is Cauchy distribution. Generate is Cauchy. We are doing Cauchy distribution here. So first pass R norm, t rows are columns, then introduce that you need t rows and r columns, then you create the matrix R student. Again you pass t rows and r columns divided by square root chi-square mu new square root of chi-square t rows, because this was what we needed. What are we doing actually? T distribution, right? Chi-squared value is divided square root. New, this remains the same. Chi-square distribution, y minus nu divided by root over 2 nu, y minus nu divided by root over 2 nu. So square root of nu, chi-square divided by nu, chi-square divided by nu. So square root of nu, okay, then z, mean divided standard deviation. Column means, this is column mean, and you're applying, oh my god, so many things. Standard deviation on the second, which is column. Standard deviation, apply r stud 1. We're applying on this first, on whom? On r stud 1. We're taking the columns of r stud 1 and applying standard deviation on them in column means of r stud 1. So that's it. That was Cauchy distribution. Okay, that was Cauchy We just did Cauchy distribution, not the T distribution. Now this is the T distribution, TR and TR square. So same thing, our student's T distribution equation remains same, but just in chi-square is TR square plus random TR square nu 2. Because nu 2 we have to do it twice, that's all. Everything else remains same, very easy, that's it. Nu 3 we have to do it 3 times, that's all. Square TR square, you needed to do it 3 times, right? You did make a mistake here. Then you created the matrix. You could have made the matrix much later. This is replicating 2, so this is a mistake in this equation. Anyway, that's it for T distribution. Next problem is simply chi-square distribution, asymptotic normality. This exercise demonstrates the asymptotic normality of the sample mean and the population distributions as chi-square distribution. 5000 samples, replicated T equals 5, nu equals 1 degrees of freedom, and this is the equation for the chi-square distribution. Very simple, small program where this is it. You pass in 5 observations, 1000 replications. You create random numbers, 0 in between 0 and 1. Then you create chi-square squared, which is random number squared, just like the previous T distribution problem we have seen. It was much more catchy, but this is because it was random number. If this was random number, this is R norm. No, this is random number, this is random number. Both are the same. TS squared, though this is in 0 1. We're not doing chi-square, so we're not squaring the random numbers, rather we are keeping it uniform. Beautiful. Then in chi-square, okay, we did it directly. We are squaring the random numbers. Then we are doing z, which is square root of t multiplied to mean of this chi-square minus 1, because this is 1, mean of chi-square minus 1 divided by square root of 2, but nu is 1, so they didn't do it. Column means, so we don't have to transpose it because we use column means. So we're taking column means of r chi minus 1 square root of t, very simple. And then we simply do a histogram with 21 breaks. In R we need to mention that we need 21 breaks in histogram, that's all, very simple. Z sort is sort, we just want to sort the data, very simple. Now we have done a lot of stuff. Finally an application, which is portfolio. Let's see if there is any theory we need to know about in portfolio diversification applications. Some of the key results from this chapter are now applied to the bivariate normal distribution. The first application is motivated by portfolio diversification problem in finance. Let y1t and y2t be jointly IID random variables with means, variances, yt minus covariances, and correlation rho equals sigma 1 2 divided by sigma 1 2. Bivariate normal distribution is 1 by or twice by root over sigma 1 square sigma 2 square 1 minus rho square 1 by twice by sigma square. Exponential of minus 1 by 2, just remember this, 1 minus rho square whole square minus 2 rho minus row. This one remains same all the time. My 1 by 2 square this one. Which a lot of parameters are unknown. Mu1, mu2, sigma square. The shape of bivariate normal distribution is shown in figure 2.7. This is portfolio. Oh no, what I'm doing. I wanted to do portfolio diversification. I'm sorry. A fundamental result in finance is that risk of portfolio can be reduced by diversification when the correlation between the returns and the assets rho is less than 1. In extreme case, rho equals 1. When the correlation is low, risks diversified. So we have scatter plots, we have apple and fold stocks. A common assumption underlying portfolio diversification model is returns are normally distributed. In the case of two assets, the returns are apple and fold. Pairs observation function is log likelihood function minus log twice 1 by 2 log sigma 1 square sigma 2 square, because there are two inputs here. Log of 1 by minus rho square minus 1 by 2 1 minus rho square t z1 square 2 rho z1 z2 z2 square, in which z is the standardized distribution y and t. Maximum likelihood estimator theta hat. The first order derivative of the log likelihood function is first derivative this one, setting this to 0, rearranging else. Mu equals this sigma square rho. We have to remember rho 1 by t. So just evaluating these expressions with the estimate of the covariances. Now we have to estimate the covariances correlation positive elliptical shape of scatter plot. To demonstrate the potential advantage of portfolio diversification, define the return on the portfolio of two assets. This is which are respective weights on apple and fold with the property they equal to 0. The risk of this portfolio is this equation. For the minimum variance portfolio, solution is minimizing W1 W2. Optimal weight of apple is 1 to covariance, variance of apple minus total covariance plus total variance minus 2 covariance. Sample estimates we can afford for 1 minus W1 is an intimate risk of the optimal portfolio is on the W1, W2 estimate of risk or maximum population. The risk on the at this for proves advantage of portfolio diversification. Keeping this in mind, 44, let's go to 49. Portfolio data files, apple and fold, 2000 observations, sensor IID, normal distribution, means are 1, variances are 4, correlation are parameters initialized with this maximum likelihood estimator. We need to find these parameters, compute portfolio containing this, let the return on a portfolio containing this is the return. Risk, we need to derive risk. Okay, let's see for portfolio. First we'll start with portfolio diversification. Let's look into diversify. Is there any local function? No, there is no local function basically, so this becomes quite easy because there is no local function. Let's do diversify here too and let us see. Okay, first as usual we are creating and removing remove object, then we are loading data in which we are taking up to 2413 observations. We are calculating percentage returns. Is very easy in MATLAB. 100 multiplied to taking difference of log d log. How is done in R? We need to pass the information in a function called doing the differentiations. If I'm talking about as matrix, I'm not sure who is doing the differentiations here. Matrices. Use as matrix attempts to turn its argument into matrix. Okay, and row and column by row dimensions. We know this already, but we don't know how am I calculating the returns. Okay, I am doing it in two steps. First, I'm putting the detailing as matrix, then I'm doing, oh, it's very simple. This is simply passing, we want them in matrix. This is this line, and then 100 into differentiation into log of is the same thing. Then we need to do statistics, mean, median remains same, RAPL minus mean of RAPL square, mean of RAPL minus M1 squared. What was that? 48 row? No, 44. Okay, portfolio. Ripple minus mean of ripple squared. This one, yt minus mu squared. Yt minus mu squared ripple is sample mean y minus mu minus population mean squared. Fort minus population sample mean minus population mean squared. Correlation coefficient. So I'm finding the correlation coefficient between them. Concatenate and print. Compute weights and risks. Oh, that's all for the first part. Oh, that is very simple. So 43, let's go to 52 again. Interpret the shape of each distribution. That's all. Okay, anyway. 43. No. 40. Oh yeah, this is it right here. Okay, compute the weights. Weights are given. Where are the weights given? The weights are given here. W1, W2, weights are given. Where's W1? This is W1, where W1 is sigma square variance minus the covariances divided by total variances minus 2 covariances. Variance row 12 is correlation multiplied to covariance is, first I'm finding covariance. I think I did it directly here, finding the covariance, which is r square root of S11 into S22. S11 and S22, we have S11 the means. S11 they are the means. So rho is the correlation. Rho is the correlation multiplied to square root of the means multiplied. Correlation multiplied to the square root of the means. Okay, square root of the means, that is covariance. Yes, rho correlation multiplied to square root of the rho square root of the means, S11 and S12. That is covariance, variance, standard deviation. Yeah. So minus the covariance, this covariance, 2 into covariance. We could have done that for MATLAB too. Rho is simply rho multiplied to square root of mu1 into mu2. Very simple. W21 minus W1. See, rho sigma 1 sigma 2. That's all. It is very covariance is very simple. Rho multiplied to square root of sigma 1 sigma 2. That's all. Root over is root over because they're squared otherwise. Oh, I just want to remove the square effect. So covariance, that's all. We're just taking then S2 portfolio of the second one. Portfolio of the second one. See, this is covariance, optimal portfolio. Then comes the portfolio of the second one, which is weight 1 multiplied to the mean, weight 1 squared. This is weight 1 squared multiplied to the mean. This is weight 1 multiplied to the mean. Weight 1 squared plus weight 2 squared. Okay, this is this equation, right? This is the equation. Okay. Weight 1 square mean, weight 2 square to weight 1 weight 2 covariance. Weight 1 square mean already squared. This is squared mean. Weight 2 squared to the mean covariances. Okay, that's great. Graph, just fold an apple. That's all. Scatter plot. It's a scatter plot actually. Did we pass it? Okay, let's run this one. Let's see. Very simple. Okay, that concludes the chapter today. Thank you very much for your patience. It was nice, great to have you all here. Really enjoyed. This was the biggest chapter, I guess, in total econometrics, and we were introduced with a lot of stuff. We were introduced with chi-square distribution, t-distribution, normal distribution, Poissons, and a lot of many stuffs that we will might not be repeating, but maximum likelihood estimation, especially the gradient and Hessian discussions, we will be continuously needing them. So thank you very much for your patience with me. It's still running, still busy. I'm not sure how long it's gonna take. I hope it looks good. The portfolio diversification, gradients, the portfolio plots. Anyway, we have learned to do diversification, which is not bad. We can do R, if not MATLAB, for this purpose. Thank you.